Electrons and protons, dear little wizards, moving hither and yon, sedate we particles, more firmly fixed. Long did you escape our eager quest, Archimedes, Pythagoras, Plato, and the rest, Galileo, Torricelli, Newton, and Boyle, Franklin, Priestley, Lavoisier, and Scheele, Davy, Dalton, Cavendish, Avogadro, Berthollet, Berzelius, Dulon, Petit, Liebig, Walker, Gay-Lussac, and Faraday, with uncounted numbers of learned ones, knew not of infinite littleness of you. But now even the schoolboy knows you. We all pay homage to you. We greet you, we praise you, we measure you. We form our theories in terms of you. Of you, yet essence of rocks and gems, of grains and flowers, of beasts and birds and men, we praise you, yet all of earth and moon and stars, the universe is made of you.
I like that one.
Me too. That was a poem called Electrons and Protons from a book called Laboratory Musings by Dickinson, but not Emily Dickinson. Rather, is Laura Dickinson, who was born in North Amherst, Massachusetts, on November 15, 1870, and essentially was a missionary and physicist. And she is tangentially related to the well-known Emily Dickinson, third cousins through their great-great-grandfather, as you can see, if you can even see this family tree right here. So, and this poem was actually on the American Institute of Physics, AIP. So on the website, I'm going to share that shortly. But before, what else can we say here, really? Some people may be wondering, what is this? Exactly. So there's always that question of what this is. In case you're wondering, this is SG2 on Space, the only weekly space show. Hopefully you're watching us on youtube.com/@shingo/streams. Remember, you can support the show on patreon.com/SG2onspace. This disembodied voice in the background that you just heard is who?
Hey, Shen.
Hello. It is Dr. Leonard Kramer with his signature headband.
It matches my green. I picked a green
one.
Which
always matches whatever outfit he happens to be wearing.
It's kind of a greenish blue, I guess. So I accessorize.
it works pretty well. So I can't remember what you were last week, but it was something different.
I don't know. It might have been my red one. I don't know.
I think so. It seemed a little more colorful. But this is the SG2 on Space, the only weekly space show with your hosts, Shinga and Leonard Kramer. And honestly, this is episode 181. Wow. Last time we talked about Richard Feynman. This time we are dabbling into not a human, but a type of particle or fundamental part of nature, namely the electron, which sounds like something in that poem where you're like, oh, probably heard it since I was like a little kid, right? I mean, everybody knows that these days, or at least in school, you're supposed to learn about it. But there's actually a lot more to the electron than meets your eye, which Dr. Leonard Kramer knows a lot about.
Oh.
So, right?
Right. So you're going to ask me, so what is an electron?
All right. Well, why don't that would be the standard way to ask you.
Oh, you can do something different.
I could ask you, what is something like maybe what is something about the electron that most people don't know about?
Most people don't know that they have a property called spin. Most people don't know that they don't appear to have any size to them that we are able to discern. They are they are very small compared to the nucleus of atoms. Exactly 1,830 times smaller than a proton, and there's some mysterious things about them. One of them is, I think I mentioned self-energy to you the other day, and the idea is, well,
Yeah, that's actually that's something I've not apparently not heard of before. What is self energy?
well, ordinarily, if we think of well, background. Okay, electrons have a negative electric charge. They're responsible for electricity, mostly the current that flows in the wires in our house. They flow through the copper conductors or metal conductors that we use from day to day, and they are particles. The that was established in the late 19th century, but the thing is, we don't seem to they don't seem to be subdividable. In other words, if we collide electrons with another electron or with something else, we don't see any pieces coming out. We only see electrons, and the charge remains. So they have an electric charge, a negative electric charge, protons, and have a positive charge. The charge is equal. So ordinarily, classically, when we think about an object that has an electric charge, we bring all the electric charges from infinity and bring them all together to a point, and so we compress them into a certain amount of. It requires a certain amount of potential energy to assemble the charge. Well, it doesn't work with electrons. It doesn't. So there's the mystery. The mystery there is that there doesn't seem to be any radius associated with the electron, and that it appears that the amount of charge that if we were to assemble it from, say, some kind of sub-electron, that it would take an infinite amount of energy to do that. So that's a very peculiar situation. They also have what's sometimes you'll read about something called spin. So
Right.
the electron and the principal evidence for that is that they exhibit a dipole character, magnetic dipole character, when you put them in a magnetic field. But there's really very essential um, mysteries that surround or that are encompassed by quantum mechanics. So here you brought up a paper about the self energy. I remember
Well,
coming across this
mhm.
in graduate school when I was studying classical electrodynamics, and the professor, his name was Wolf, and he uh, he talked about self energy, and that the electric charge itself. In other words, you can integrate the amount of energy that's in the electric field from the electron or proton,
Mhm.
for that matter, and that doesn't seem to participate uh, in the dynamics or the electrodynamic the dynamics of the particle. So we know that energy has a mass associated with it. Electrons certainly have a mass, but it doesn't seem to be related to this energy having to do with the self energy. And we don't know what it is because we need a radius. In other words, we need to bring all of the particles that make up an electron
So
into a certain
the,
volume of
the,
space.
yeah, in what is it? So in like basic, I don't know, science class or whatever in elementary school or middle school, they just assume like electron is like a particle
Right.
of some
And
size,
and
but
and
that's
and
not
yeah,
accurate at all.
right, when you study this, probably in high school, you'll study
Hmm.
this. You'll just, oh, there's this thing called an electron. Yeah, yeah, okay. But they don't tell you that there's these really strange things that are going on that nobody understands. Um,
So it's
so
interesting what you're saying,
so
right?
yeah, and so there's also a property called spin. Um, that has to do with angular momentum, and so they're really not spinning. There's nothing that can be spinning since there's no radius that we can discern. um, and I think one of the physicists from the 1920s,
Hmm.
I think it was Dirac, who said, "Look, this angular momentum." I've kind of changed gears here, but we're talking about angular momentum. Angular momentum has to do with something where an object is spinning, and charged particles do reflect this in terms of some kind of current loop that's associated just intrinsically with the particle. But he said that, well, if we make an assessment about how, any kind of reasonable radius that the uh, any kind of guess at the size of the radius of a electron the surface of it would have to be moving faster than the speed of light in order to account for the magnetic moment that they exhibit. So they're not there's a fundamental if, I say, so how do you know about this? Well, we don't. I mean, what's the explanation for this? And I think nobody does. I think that
So
it's
what? Huh? Oh yeah,
yeah.
go on. Sorry, I don't want
So
to
it's
interrupt
almost
you.
like the electron is some kind of singularity. I guess there is people who are into string theory, and they think that
Hmm.
if you get down deep enough that there's a string down there somewhere. But we don't have the particle accelerators powerful enough to be able to collide two electrons together with enough energy to break it apart or to exhibit any internal structure to it. So it
This
doesn't.
is
It
interesting.
has an electric charge, and it has a spin.
Ben,
And I always get this confused. It's a boson or a fermion. So I think they're fermions because its spin
electrons,
is
fermions.
uh, a integer half. You
Yep.
know, it's a
Spin
half. So
classification.
that means its spin is h bar over 2, or we just say spin 1/2, and it's plus or
Electrons are
minus.
fermion with electron spin 1/2.
Yeah. So it has and so fermions are particles that have integer multiples of a half of a angular momentum unit. The angular momentum unit is Planck's constant divided by 2 pi. And
Right,
sometimes
right.
you'll see people say h bar because they
H
write it
bar.
they
Yeah.
write a little h, and I don't even know where the H comes from. They just, it's Planck's constant is H. I don't know why it's not a little P or for Planck or something. But anyway, it's Planck's constant, and he used the letter H, and then because H over 2 pi appears in the equation so much, they decided to just call H over 2 pi was equal to another
Yeah.
symbol called H bar. So so there's funny things about it. If you this angular momentum thing that we're talking about, it's quantized, and so no matter what kind of measurement you make, you'll always measure a half, either plus or minus a half. You won't measure,
This is what you're talking about, right?
yeah, for the electron spin. And so in the 20th century, early 20th century,
Hmm.
um, there was a theoretical physicist named Stern, and experimentalist named Gerlach, and so they invented this thing called the Stern-Gerlach apparatus, and every physicist
There we
who's big
go.
in quantum mechanics knows about this. And so what they did was they took an atom. All right, so this is an atom, and it has one unpaired
Hmm.
electron in it. So it's a heavy atom, right? That has the spin of one electron, and it has a lot of electrons in it, but all of the electrons are their spins are all balancing out except for one. And so this one electron that's in the outer shell and it doesn't have any angular momentum of its own. If you spray the gas of this material through
Hmm.
this inhomogeneous
Homogeneous.
magnetic field, it
Right.
the beam splits in two. Now this is not an ion beam. This is a neutral. It's a
Why does it
neutral.
split in two?
Well, why does it split in two? So we're going to get to that. But this is the Stern-Gerlach apparatus, and they always use silver because silver has for the working fluid or the gas or whatever you call it, because it has certain properties that make it convenient. Okay, but
Hmm.
and I've never really heard people talk about this very much, but silver has one electron in its outer shell that when you chemistry chemistry is kind of bad because they, chemists just memorize things, right? And so they don't, you know,
I mean,
so you
that's I remember doing that. Just like,
yeah, so
oh,
you
it's
remember,
the outer
oh yeah,
shell.
it's the
Yeah,
S shell, it's the P shell, and then it's the D shell. And so
you shell.
physicists don't need to memorize it because they
I mean,
they
good
know
point.
about the wave mechanics and stuff like that. The only thing they have to memorize is that, well, the S is the S and the P shell, but the reason for using those is sort
Hmm.
of um, anachronistic. But anyway, so you take the silver, and like I said, I think you could use copper, or you could use gold, or a number of other elements that have you could use hydrogen actually for this hydrogen. So because it has one electron, one unpaired electron. And so when it goes through this inhomogeneous magnetic field, the beam splits. You don't get a and then the silver will deposit well, they have a photographic plate. I don't necessarily think it needs to be a photographic plate. I think it could be like glass or
Right.
or something like that. And you'll see some gray silver, and it splits into, makes a little kiss kind of shape there, except that this is it's not two lips, it's just like, like a little oval thing. Right.
Right.
And so what's happening there is the expectation is that you just get a blob, right? And they
Yeah,
didn't
because you're
even,
shooting these
yeah,
particles.
they didn't
Yeah.
even actually show it right, because you see, they have the little diagram, the classical expectation. Classical expectation, you wouldn't even expect it to be elongated like that. You just expect to have a spherical or a circular blob of
Oh, okay. I see what you
they,
mean.
so they
The
have it
experimental
elongated.
actual result
Yeah.
is like two lines, well, two
Yeah.
curved lines.
So it ends up being kind of curved lines because you can't make the field perfectly, uniformly inhomogeneous. That's interesting. But there's some structure to that as well. But the reason it goes like that is because, for some mysterious reason, that one electron that's going through this gas is affected by its magnetic moment. Its intrinsic magnetic moment
Hmm.
is affected by this field, and it's pulled in one direction or repelled in the other direction because the field is inhomogeneous. And so it only exhibits these two um these two magnitudes of the moment of inertia, the magnetic moment. So it either goes up or down, and it's exactly 1/2 h bar. And so you can do all this math and stuff like that in there, but
This
that's
is what it's
that's
saying, right?
that's a
Right there.
very mysterious kind of thing. And keep in mind, this is a neutral stream of gas, of vaporized,
Yeah. So
silver
like
vapor.
the
Right.
silver, these it's shooting out these silver atoms,
Uh-huh.
which are neutral. It's not
Yeah.
charged,
And I think this
yet
isn't
it
an
deflects.
evacuate it's in an evacuated contain, um, like
Hmm.
it's in a vacuum, just so there's no air in there to screw things up, to collide with. But
Right.
so there's this beam. And so that's the demonstration that it's quantized. And so there's all kinds of interesting things about this that people have been studying for many years. So when you take quantum mechanics, the professor will start talking about the Stern-Gerlach apparatus, and it's kind of like a polarizer. Like it will split the two beams. Half of the atoms have a spin up, and half of them have spin down, and there's no intermediate, right? And it's just very strange. It's very frustrating,
Wow,
to think about.
that's interesting. How does the electron obtain a magnetic moment
Right.
if it has zero angular momentum and therefore produces no current loop to produce a magnetic moment?
Yeah.
The postulated electron had an intrinsic angular momentum independent of its orbital characteristics.
Something like that. So that's the kind of things that they discovered.
Electricity, but it's not
Mhm.
even actually physically spinning. It's
I
doing
think that
something.
I think physicists, I think I would be uncomfortable saying that it's physically spinning. But they do call it spin. So it is some kind of angular momentum. Um, and that's all I can tell you about it. Right? I don't think there's any
Right.
deeper. I don't think if Feynman, who we talked about last week, if he were here, I don't think he could give us any deeper insight than that.
Yeah, and why is it discretized?
It's
So,
discrete, and not only that, but suppose you run it through. You run your beam, your atom beam through the Stern-Gerlach apparatus, and you divide it into two beams, and then if you take one of the beams and you run it through another Stern-Gerlach, we'll call it an SG apparatus, it will not split again. It'll just continue. You know that you've prepared it in a spin up or a spin down orientation,
oh, I see.
right? So it'll do it again and again and again, and it doesn't ever affect it. It won't split again if you run it through this. So you
SG
definitely,
is my name, by the way.
that's true. So yeah. So but but so that's interesting. So let me repeat what I said. So if you run the atoms, the gas through the Stern-Gerlach apparatus, and you divide it into those two beams, right?
Yep, two beams.
And then just throw away one of the beams, right? Just block it or something. So now you have a beam that's prepared electrons, and it's not really electrons. It's just that one electron that's that one unpaired electron in the silver atom. So you've prepared it into like, let's say, a spin up direction, and then you run it through an identical apparatus. It will just continue. It will just go through. It won't split again. It'll just continue on through the way it was before. So you won't have a further splitting. However, if you were to so if you were to prepare an up beam, a spin up beam like that, and you ran it through another Stern-Gerlach apparatus that was rotated, let's say 90 degrees, the axis was rotated 90 degrees, then it would split again. And it would split. So in this case, the one we're looking at, let's say that spin up and spin down is along a z axis that we've designated. Right?
Okay.
So,
I see.
and then you had another Stern-Gerlach apparatus that was rotated so it would split the beam along the x-axis.
Yeah, so it was
then
like that.
that beam that you had prepared in the up direction, in the z up direction, it would split again into a plus and a minus x direction. And so it's like it doesn't really have it's and then the z component of it just disappears. It just becomes, it doesn't, it won't be in that z up state anymore.
How do you explain that?
It's a fundamental mystery about quantum mechanics. It's one of the elementary problems that was discovered in the early 20th century. So how do I explain it? I don't explain it. I can do the math.
Do the math, and there we go. There you go.
This is a property of nature that electrons and protons and neutrons also have this property called spin. And then there's another interesting thing about it. What it does is, because these are the fermions, so no two electrons can be in exactly the same state. And so when we talk about two electrons when we talk about two electrons that are paired together, so they have opposite spin, and they don't, and that's all you can say. No matter what measurement you make, they'll just be opposite, right? So they'll be an opposite. So those two will pair together to form they kind of bond together. And so in chemistry, you learn about these orbitals and such, where you have two electrons in a shell and so forth. But it means that the electrons can't be all in the same state. You can contrast that to bosons. So photons,
which could be.
Photons are bosons. And so, in this room, or in the room, when you're walking around, there's light particles. Photons are just running all over the place, and they can all cram inside the same area. And and so that shows that photons and which are bosons, they can all be in the same state. And so you don't have that problem. But electrons in particular, they can't be in the same state. And so two can have the same energy if they have opposite spins, but then
Right.
you can't, if you try to put another electron in that volume, then it will do something else. And so, for example, and so that's the explanation for all those orbitals and things that you
The stuff
memorize.
that we learn in chemistry is based
Right.
off of this quantum
And if
mechanical
it wasn't for this, and
principle.
you got it up there, Pauli exclusion principle.
Exclusion
If
principle.
if it
Yeah.
wasn't for that, then then matter really wouldn't work. I mean, it would mean that, like, when I bring my hands down, my hands would just pass through each other, could pass right through each other. But because of the Pauli exclusion principle, then I can't really push the matter together, right? And that's a kind of explanation for why matter has,
No
substance. It
two
doesn't.
fermions can exist in identical energy quantum
Right.
states.
So they can get as close as the same energy levels and the same angular momentum, but they can't have the same spin. And so they will force themselves into opposite spins. And so that's the name of that tune. Electrons are kind of neat. They were really discovered around 1870. People were playing with cathode ray tubes. Cathode ray tube is like the old time television. I
Tell
don't
me
know if you
about cathode ray tubes.
are you old enough to remember television when there was a big tube? You know?
Uh,
No?
yeah,
No,
actually I
probably not.
do. I was
Yeah.
born in the, you know,
Yeah.
late 80s, so I do
So
remember that.
so in the old days when we've had television for, like, I had television when I was growing up, most of the time. It was black and white, early on, but um because my parents didn't buy a color TV for a long time. But um never mind. Never
Well,
mind.
I mean,
All right.
good to
Uh,
bring that into the
yeah.
story here.
So
Yeah.
so anyway,
That's what
this
you're
is
talking about, right?
it's basically a television tube.
Yeah.
And so, but and it was just kind of invented. Television wasn't invented, but this thing was invented in the around 1870 um, by a guy named Crook, I think. Crooke. Crook. I don't think he was a bad guy. That was just his name, Crook. And I'm thinking of Richard Nixon saying he wasn't a crook. People, but
Crooke. Go on.
yeah. And so he was playing around well, when you heat the cathode is the negatively charged terminal there. When you heat that up and you bias it negative, so you make it negative, then um, people observed like some glowing gas emanating from it. And that's the electrons. Well, we now know that's electrons that's striking some residual gas it's an evacuated tube. But he did some neat things with it, like he put an obstacle, it's called the Maltese cross, in there. uh, and I don't know why he picked that shape. I would have picked like a little dinosaur, probably, or
This thing, right?
yeah. I
That
don't
that
know.
thing in there. Yeah.
Yeah, I don't know why he put
Oh yeah,
that in there.
like right there. This picture.
Yeah,
Yes.
I would have put a peace sign in there. But anyway, he put that in there, and then he observed that it cast a shadow. It cast a shadow from the electrons, and he didn't know that they were electrons. A lot of people thought this was some kind of electromagnetic wave, because Maxwell, had discovered that light and all these light and different kinds of radiation.
Right.
It's definitely a kind of radiation. They called it cathode rays because it was coming from this thing called a cathode. I don't know what the
Cathode
etymology of the
rays
word
are
cathode.
actually, you're saying they're just electrons that
Yeah,
somehow
they're
causing the
just
air to
and
glow.
they used to call them cathode rays. And I don't even really. I was going to say I don't even really know. I have to look up the etymology of the word cathode. It
Are
must have
streams
something.
of electrons observed
Yeah.
in discharge tubes.
Yeah. So people started. Then there was a guy named Thomson. Okay, and really the electron should be. We could actually call them Thomson particles, because he's the one that figured out that. Yeah, he didn't photograph well. I, but
It's
um,
not the
I,
greatest photo, but
yeah, but
okay.
I believe he was a good guy, though. I don't think there was any. But anyway. What he did with it, he started doing some real. Oh, before I get it onto that, Crook, I think, put a little paddle wheel. Not only did he do the Maltese cross there to show that it cast shadows, okay,
Uh-huh.
but he also put a paddle wheel in the flow. like somehow they were able to do the glass, you know, the glass work so carefully. He could put a little paddle, and he showed that the electrons, when they struck the paddle, it would rotate around. So they knew that they carried a significant amount of momentum. And so there was all that kind of inference that the electrons had some mass and were
This
carrying.
thing.
Yeah, that Crook did that, right? Yeah, see,
Yeah, yeah.
Crook's paddle wheel. Um, and this was, and there was 1879, and so it was a great time to be a physicist, I think, because you could have fun doing this kind of stuff.
Well,
I
because you
mean,
didn't know what was going on.
yeah, and you don't know what, and so you get to publish these papers, and you go to conferences, and everybody's all excited
It
about
found that
it.
it rotated when the rays hit it, the paddle wheel
Yeah,
turning in direction away from the cathode site, suggesting the force of the cathode ray striking the paddle was
yeah.
causing the rotation.
And so they also noticed that a magnetic field would bend the field. Like if you put bend the flow. So if you put a magnetic field around it, and then also if you passed it through electrically charged plates, it would also deflect it. And so what Thomson did was he set up a vacuum tube like this with the cathode rays, flowing through it, and then he set it up so that he had a uniform magnetic field in one direction, around one orientation, and a uniform electric field around the other direction. And so what charged particles do in a magnetic field is, I guess a lot of people know this, they will follow a curved path. They will actually
Hmm.
circulate around in a circle. It's called a
Right.
Larmor, like a Larmor effect or something like that. Anyway, so there's a radius that's associated with that because
Oh, and how he measured how it deflected, I guess.
yeah, so what he did was
Right.
he knew how to calibrate or to adjust the magnetic field. So he knew how big the magnetic field was, and then he also knew how big the electric field was. So he had these two fields were, so the two forces were opposite. They were and he would adjust them so that they were equal and opposite. And from that he could back out that there was a velocity associated with the electrons for this particular apparatus. And of course it's dependent upon how much the electrical bias is on the cathode, not so much how hot the cathode is. They only make the cathode hot so the electrons will kind of like, get thrown out of the surface.
He
But
he was the one who came up with what I recall from school called the plum pudding model.
plum pudding model, yeah, I kind of
Pudding,
remember that. I was never very much impressed with that. Maybe mainly because I didn't know what plum pudding was. But
I don't
my
think I ever had it.
my mom
It's
never put plums in the pudding. So I didn't know. I
but
didn't- you know, but
it's assuming that the electrons were embedded in some
uh-huh.
positive charges like
Yeah, raisin
raisins
bread.
in
I
plum.
think it should be a
Yeah,
raisin bread because I know what that is.
right,
So,
right. Of
so
course, that this is shown to be not true these days because
mm,
we just started out talking about how electron
yeah.
is so
But
strange.
I wanted to get at something. Thompson was able to measure the velocity of a
Hmm.
particular setup, and so then what's interesting about having a velocity was that it wasn't it wasn't the speed of light. It was much lower than the speed of light. And so that immediately said that this is not an electromagnetic phenomenon. And then he also played around with the radius of the curvature in the magnetic field, and he was able to back out the mass. Well, at least I don't think he could get the mass exactly, but he could get the ratio of the mass to an to a
To
hydrogen
charge,
to a proton. So he could get the mass of the proton of the electron relative to the proton, and so it was pretty stunning that it was this tiny little particle compared to
there's
yeah.
the famous oil drop experiment
Okay, so
by
Millikan came
Millikan.
along. Yeah, Millikan came along, and I swear I remember doing this experiment in high school. Okay,
Really, you dropped
and I
oil?
was even
That's
talking to a professor friend of mine who
mhm.
who also does this in his college labs, and so wait, oh, my screen just flickered there. Um, so uh,
Show me what
what
this is.
well, I actually don't know exactly what that is, but the Millikan experiment was Millikan was able to take little oil droplets, and you can do it with water
Ah, here we
too,
go.
but my
Yeah,
understanding is
this is probably a better
right,
schematic
and you
here.
let it
Look at
and you
that.
let it fall through a little hole between two electric fields, and so
Mhm.
he was able to charge those, and think these days they use a radioactive source to electrically charge them, but you don't need to do it that way. I think you can give it ultraviolet, or some, or they just acquire a certain electric charge statically from the static. So each one of those little oil droplets, and it's a tiny droplet, will
Mm-hmm.
fall through a hole, and then there's a uniform electric field. In this case, it's pointing down. So some of them will have a little extra electric charge on them. And what he was able to show was that the rate that they fell was quantized. In other words, they would go down at, that each droplet would have a charge of equivalent to 1 electron, 2 electrons, 10 electrons, maybe 100 electrons. And he was
How
able
do
to show
you? Sorry, go on.
just by accident, by like an electric charge would get attached to the
Hmm.
oil droplet, mainly just by accident, and then they would fall through, and he could balance them just like static electricity. So it was like they
Oh,
were
yeah.
statically charged.
You like
And
levitate it.
yeah, and so he was able to adjust that electric field, but the potential on that electric field, so that it would balance it, and then the droplet would not fall. And I remember looking through this little microscope aperture, and seeing the oil droplets falling. And it must have been 12th grade.
And that was so
I
this eye in your
Yeah,
example would be Leonard's eye
that would be
staring
my
into this
eye.
micro. Yep.
And and
Did you have an apparatus like this thing too? Oh, look, that's a microscope,
yeah,
right?
I think it was a little bit something like that, except
Yeah.
it wasn't quite as scary. As That's a pretty scary looking thing. Looks like a
I mean,
bomb. But
it's like here's a microscope looking into this thing. That's
yeah,
some
it's
apparatus,
like,
the oil
yeah,
drops falling down.
something from Men in Black. Like there's a little civilization in there. Remember the
There,
guys
who knows?
yeah. So anyway,
Yeah,
never mind. Um, but
that must
but
be
so
so.
so what he
Yeah.
was able to show is that that's how big the charge was, and that it was quantized, and he was actually able to measure what's called the fundamental charge, which is Q, and that's that, or E, and it's 1.6 times 10 to the minus 19 coulombs, right? Or
Yep. I
or is
believe
this a
so.
yeah? So
1 point. Yeah, there you go. The value of the elementary charge defined to be exactly this.
oh yeah, they may have done something to define it exactly like that, maybe based upon some other. I don't know. That's not really that interesting to me. That was a but anyway. So that's all about the electron. I think that's kind of all I wanted to say about it,
We
except
we
that it's
we kind of
it.
went backwards a little bit, talking about our
Well,
current lack of understanding of it, or not
right.
lack of
Well,
understanding,
I
mysterious
wanted to,
nature.
yeah, but I also wanted to relive. I wanted to relive all of that because just thinking it would have been a really exciting time. How much fun these guys had. Just
Yeah, man, look at this. Not to be confused with pitch drop experiment, which sounds like that's
I
completely
don't.
not the same, but that's
I don't
funny.
know. Well, that's Millikan. That's the Millikan experiment, and I'm sure that
Right.
there's other people who would. Oh, Thomson, J.J. Thomson. He named the electron, and the name is interesting because it's it's the word. Well, in ancient times, people knew about electricity because they had static charges, and they would get in
Hmm.
this. And I mean, really ancient, like ancient Greeks. They knew about electricity as static charges because they observed it just the way we do, right? And people had amber, right? And so they would take
Right.
amber,
Amber attracted,
right?
like this thing, right?
And
Like
amber is a kind of plastic, and it's a dielectric and insulator. And if you rub it, you can pull off a few of the electrons, with on fur or
do you have
fabric
any
or
amber?
silk. I don't have any amber that I
Oh,
can.
okay.
I don't. But you don't need
I
to
was
use
just
amber. I mean, there's like you use regular probably just plastic will do the
yeah,
same
you can
thing.
just rub it. Yeah.
Amber is a kind of amber is fossilized tree resin, like some kind of tree
Yeah.
resin. And it was known in ancient times, and so people noticed that if you rub it, you can attract it. And you think about if you're an ancient person, I mean, whoa, that's like really impressive. But
Yeah.
anyway, the thing I'm getting to is that the word for amber in Greek is electros, and I think in Latin it's electrum. So he called it. So I think Thompson, J.J. Thompson, I think he came up with the name for the particle because he's really the guy that discovered that it was a tiny little particle and it had a lot of properties that were like matter. But and so he called it electron because the Greek word for amber is electros. So that's where we
Interesting.
get that. Yeah, it is.
There's a whole bunch of people that looked
Yeah,
into
all
this
these people.
apparently.
So it was must have been a very exciting time, but we still don't really know what we're talking about
I
because
mean, it's
we have some fundamental mysteries and we don't know the answer to them.
I mean,
Electron
according to the
is
standard
yeah,
model.
there it is. It is one of the elements, one of the
Oops.
primary
Okay, I don't know why I clicked strange quark.
yeah,
Okay, it's right there,
it's one of
lepton.
the it's one of the primary
Wait, hold on a second.
yeah,
Where is it
primary
on here?
fundamental particle. I think it's the upper left
Right
of
here, right here. Lepton.
oh
Yep,
there. Okay, yeah.
yep.
So so and we don't know anything else, but we know that there's some very peculiar things about it, namely this self energy thing. It's like how do you assemble an electric charge, even if it's a tiny little electric charge, down to a point, right? So
There is no actual point, right? That's what
there
he's saying.
well in my mind there must be some kind of point.
You do the
Okay,
point self energy tending to infinity.
yeah, but
So
it the
there's a finite. I don't know. I guess it's not a well defined radius. Not sure.
Well, you can take the mass because it does have a mass, and then maybe infer some size associated with that. But
Right.
I don't I think people have been looking at this for for many years and
Well, it even says
nothing
right
has really
there.
popped out.
The
So
admission of the hypothesis of a finite radius of electrons incompatible to the premises of the theory of relativity.
thank you.
On the
That
other hand,
I couldn't have said it better. So
a point like electron, meaning zero radius, generates serious mathematical difficulties due to the self-energy of the electron
uh
tending towards infinity.
right.
Huh.
Yes. So it means that there's something that we don't understand about physics. Probably self-energy is not relevant, that physics is doing something else.
Right.
And the
Can you
same thing
explain this part, Leonard?
what?
Where it says the electron has no known substructure.
Yeah.
Nevertheless, in condensed matter physics,
Yeah.
spin charge separation can occur in some materials. In such
Uh-huh.
cases, electrons split into three independent particles: the spinion, the orbiton, and the holon. I've never heard of these. These are quasi particles, apparently. I
Oh,
don't know if you know about
I
it.
don't know. I might have to ask my son about that because he's a condensed matter person. I wasn't aware. I hadn't encountered that before.
But what does it mean
So
by has no known
well,
substructure?
that's what I was talking about. That's what I mean. The two sentences appear to be incompatible. Um, so what that means is like if I take a proton, if I take the nucleus of a hydrogen atom, say,
Hmm.
and I hit it with a gamma ray, yeah, and
Hmm.
then it will split up into subparticles. It'll split up into protons and neutrons, and then I can do experiments with particle accelerators and do even better. And I can split them into quarks, and so I'll see I'll see
Right.
the internal structure of neutrons, protons, but electrons do not exhibit that. It appears that electron is a fundamental particle from the and that's why it's in the standard model.
Oops.
So there's no
Right.
substructure.
Okay.
And
Um, except for in certain cases, I guess, which I don't quite
I don't
understand
know.
in condensed
I'll
matter.
have to take a look at that, but I don't know. I think they're
Right.
talking about something else, some other kind of way of looking at the electron, but I couldn't. I don't know
Oh,
about that.
extremely tightly confined to temperatures close to absolute zero. Okay, so it
Oh,
must be a special condition when electrons can split into those. Is
well,
one of three
yeah.
quasi-particles.
Well, we were talking. We did do a show on superconductivity. And
This is really interesting.
in superconductivity, electrons will bind together in a in a a composite where the two opposite spins will form a kind of quasi molecule, but that's not a substructure. That's like a superstructure of an electron. And I even forgot what it's called. A
Right.
spinner, a spiner. No, I forgot what it was called. We can,
The
but
spinion? I don't know.
no. So
Okay. This is really this is interesting, but
you didn't
normally,
know that all of this was. You didn't know that there was so much interesting things having to do with electrons.
yeah, I kind of figured we already figured out what the electron is. I mean, who would have
No,
thought that we don't actually understand it?
no, it's big, serious problems. Nobel prizes that could be won if somebody could figure out, the answers to some of those questions. And the two things is what, like that self energy that we were talking about, and the idea that it's a point. That's
Yeah, which it can't possibly be a point.
yeah, that's so creepy. And then the string theorist people think that there's a string down there, or some kind of loop, but the only way to demonstrate that, or to do experimental work, would be to have some kind of particle accelerator. But I have a feeling the particle
How
accelerator
would
would.
you find that?
Well,
Like how
if you could raise the electron up, two electrons, and collide them together with enough energy to make them break apart. But I have a feeling that you would need a particle accelerator that would be something like the size of the galaxy. Um, and I'm not exaggerating.
this
You
doesn't sound feasible.
Yeah. Um, so
String theory says electrons are just like what, strings?
I
Well,
I
actually all these
yeah,
particles are, right?
yeah, all particles are some kind of string, and the string manifests itself in extra dimensions that close on the inside of our
It
the
sounds
structure of space time.
crazy.
and 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 so it appears to be falling out of favor now, because it's not fruitful. It's not predicting things. um
If your theory can't predict things, then
yeah.
it's not a very good theory.
So they talk about, well, you can make some testable hypothesis, but it seems like there's very many degrees of freedom, and so you can tune them into different ways so that they will fit whatever observation you have. And I would think that a good theory, string theory, kind of predates. It comes before dark matter, or before our real profound understanding that there was dark matter. But string theory did not predict dark matter, and that, to me, that seems like a major failure, because a theory of everything, a theory that can predict things, it would predict something like dark matter, because dark matter is so profound. It's most of the mass
Right.
of the universe is made up of this other kind of stuff that we can't observe. So
So in a
anyway.
sense, because it's not able to, it didn't predict that. It's not
Well,
a.
that's my
Yeah.
observation. I mean, I could be corrected on that. Maybe somebody has some idea otherwise, but it
Well,
just
you can
seems
come
to
up with
me,
it. Right.
yeah. So
Understood.
I think string theory has been kind of like falling out of favor, and it would be good for people to maybe work on something else. It's not my field, but anyway. So electrons, they're
Do you want to? Do you want to see one of the videos which I like to put up?
Sure, of course. By the way, I saw a UFO the other day. I sent you a picture of it.
Yeah, it was not very believable, but
No?
cool.
What
I
do you
mean, it
think
looked
it
like
was?
a blimp of some kind, you know.
Yeah. I actually
Uh,
shouldn't have mentioned it, because I don't think we didn't
let's see.
prepare to show it, but let's
So I'm going through this. So supposedly, you tell me what this is. Let me expand this. I have not seen this video yet. This is supposed to show. I guess somebody took this from on a flight from Denver to El Paso,
well,
and I don't know. Got way too excited by whatever that is. I don't know.
yeah, I see that. We don't usually use, bad language like that.
No, we don't. So you can ignore whatever it says here.
Okay.
And okay, and is that it? That is
I
like
don't know.
the worst. Wow, this is not believable. Okay, I'm just gonna read this. So this is what this image looks like. That video clip
Yeah.
essentially seemed to be a few seconds of just look that kind of image.
Uh-huh.
Um, so this was what was it? April 22nd, 2023, right? So,
Yeah.
and I don't know if they're
Yeah.
using the blurry technology, I
Yeah,
think.
well, so the other day, like, I saw a blimp. That's what we were just talking about. So I saw the blimp. I was outside of a retail store,
Right.
and I thought, oh yeah, it's a blimp. You don't see a blimp every day, and it was heading over. We live in a place we're near Ellington Field, Ellington Airport, and so I think that's where they were flying from, and it was just an advertising blimp. It was advertising a sporting goods store uh, around, and so I made the point when I took the picture because it looked,
Hmm.
it looks unusual, right? It's a
Right.
slowly moving kind of oblate object, and I made a point of taking very careful photos of it, very carefully hold. I actually took a little bit of film of it also with my camera, and I very carefully held the camera so that it would capture it for a long
Hmm.
time and was clear and everything. And I was thinking, what I really need to do is I need to shake my phone,
Oh,
right, and make it blurry, and then just go off to the side, and so nobody will be able to see really what it is. And
what it
then
is.
and
And
then
then
I
you'd be
can
like,
say,
this is a UFO.
then I can
Yeah.
give it to Shen, and Shen can talk about UFOs.
Yeah.
So that
Yeah. I
I
mean,
saw a
you could have
UFO.
done that.
I did
I
not
mean,
see a UFO. I identified it. It was a
you
blimp,
did. You identified it.
and it had advertising on the side,
What do you think of
and
this, though?
I think that's looks like clouds out the edge
I
of a
mean,
window on the side of a
and then this
side
one,
of a plane.
that thing. Is
I
that
don't
strange? I
know.
mean, these are the clouds, and
A
what is
strange looking
this?
cloud. Yeah, that actually does look like something, but it's always blurry. It's always difficult to see. You don't,
I
the
mean, this
little,
was from the ground, right? So it's like, if it's a
well,
cloud, so this is like you took a picture here, and then like another picture while you're in the air. You know what I mean? It's kind of
yeah,
strange.
I don't
Last one
know,
like
but
this.
I'm always disappointed.
Yeah.
They It
So
that
I don't
actually
know.
even could be a reflection in the glass. I don't know. It seems like it seems like the end of the wing is dark, and it's strange that the the object is right above the wing. So I don't know. I just
But
don't know.
yeah, I don't know.
It
So
doesn't
this
look persuasive to me.
supposedly this was 2012 that this was
Yeah. So yeah, why
taken.
can't people take clear pictures of UFOs? Like a picture where like the gray aliens, like
Yeah.
they're looking out the porthole and waving or something.
You know
Or
what? I'm gonna have to spend a bit of time digging through the internet and finding all the clearest pictures possible of UFOs or
well,
even aliens,
yeah, well, I think
supposed aliens.
the internet is probably
I,
the place to look
in-
for that. I
like
mean,
like
that's
like like just
source of all
there'd be
truth.
some kind of a or actually it'd be good if somebody writes up a algorithm which could process all these images and essentially reject the ones that are blurry, and you only get to keep the ones that are unidentified
Why don't you
and
ask Chat GP or
yeah.
whatever it is? What is it? Chat GP?
Yep.
Chat 4, chat something,
could
GP4.
could do that. Yeah.
I haven't done it yet. I haven't played with the chat thing yet.
I gotta
I
find out somehow, and I don't know the password, and so I
Oh,
probably should figure that out. I haven't
yep.
used it in a month or so now. But Leonard, that's
Shen,
all right. So with that, we are. What do I always say?
look up because you never know what you'll see.
Yep,
Of
that's
course,
right. Look up because you never know what you see. You've been
but if you
watching SG2 on Space, the
if
only weekly space show. Thank you for watching this sports show, patreon.com/SG2 on Space. Remember also that we do put some of these episodes on Spotify. Typically, the YouTube
Excellent.
ones are more up to date, but you can go there if you wish to listen to the audio episodes, which I will put on later. Thank you to supporters Kyle Baker, Sam Welsh, and Atum Ra, who I'm always going to give credit for doing this show for over a year and a half when he was, when I was not controlling this in the background. So with that, we will be back next week. And what are we talking about next week?
I don't
Well,
know. We'll think of something.
we will think of something. Next week will be episode 182. So I'm sure we
Wow.
will come up with something exciting. All right, with that,
Namaste
namaste
and
to everyone.
mwah.
Again.